So the purpose of our experiment is to investigate how different materials affect the transfer of heat across a solid-liquid interface and how this is linked to the thermal conductivity of the material. When heat is transferred from a liquid to a solid across the interface, the thermal conductivity of the solid is of significant importance in determining the rate of heat transfer. For example, if a solid has a high thermal conductivity, it will absorb the heat energy quickly, causing its temperature to increase while the liquid's temperature decreases more rapidly. Heat flux at the solid liquid interface is continuous, so we can equate the heat flux occurring through the solid as well as the liquid at the interface, and we will use this equation to experimentally determine the thermal conductivity of the solid material. We found the thermal conductivity of our liquid, which is water, through a Google search, and in our experiment, we're going to be determining the conductivity values of different materials like aluminum foil, styrofoam, stainless steel, and glass.
The first material we used was aluminum foil. The foil had a thickness of 3 millimeters, which is the smallest thickness of all of the materials we used. Aluminum foil also has a high thermal conductivity. Because of those, and the relationship defined in Fourier's law, we believed that the solid-liquid interface would have a large temperature gradient. Conversely, because of the higher conductivity of the aluminum foil, we believed that the solid material would have a small temperature difference.
A few moments later.
The next material we used was 1/2 centimeter thickness of styrofoam. And we observed that this was a good insulator, and because of this there was a small temperature change at the interface, at the solid liquid interface, and a large temperature change at the other side of the boundary because heat was not conducting through this good insulator. Contrary to this, the stainless steel we used was also a 1/2 centimeter thick, but it was a good conductor, and therefore we actually observed a larger temperature change at the interface, but a smaller change in temperature at the other side of the boundary, which is the results we'd expect for these materials.
The final material we used was glass. Given its lower thermal conductivity, heat transfer was less efficient, which led to a larger temperature difference within the glass material itself. Furthermore, the larger thickness of the glass at 0.8 centimeters means that, as stated in Fourier's law, the rate of heat transfer would be reduced, which would create a relatively smaller temperature difference between the solid-liquid interface.
So, based on the results that we have received, aluminum foil is the best conductor of heat, while styrofoam is the worst conductor of heat. And the reason for this is that the aluminum foil has free electrons, which aids in heat transfer more rapidly, and the styrofoam has trapped air bubbles, which is a good insulator of heat, as air is a gas. And you can see that the temperature throughout the aluminum foil is more uniform and more constant as compared to the temperature throughout the styrofoam, which means that aluminum is a better conductor of heat. And the temperature difference between the solid liquid interface and the other side of the solid is way smaller for the aluminum than the styrofoam.